Hello, and welcome back to the Cosmic Companion. In this week's episode of Astronomy News with the Cosmic Companion, we look at quark matter, a bizarre state of matter which could make up a large percentage of some neutron stars. We will travel out to the Kepler 160 planetary system, where we will examine a planet and star much like the Earth and Sun. Next, we find evidence that may help answer one of the mysteries of planets around other stars. If they are as common as they now seem, then why do some stars travel through space alone? Then, we learn how Mars, typically known as the red planet, may have also once been the ringed planet as well. Finally, we welcome astrophysicist Anna Ho of the California Institute of Technology to the program. We'll talk about her work on discovering a previously unknown form of supernova explosion. Normally, we think of the states of matter as consisting of solid, liquid, gas, and plasma. Roughly 4 decades ago, a new idea emerged of quark matter. This bizarre material would be produced by enormous gravitational forces crushing neutrons, freeing the quarks which make up those subatomic particles. This quark matter could build up, researchers speculate, forming quark cores making up more than half the diameter of some neutron stars. Kepler 160, a star much like our own Sun, is accompanied by at least 3 planets similar in size to our home world, and KOI 456.04 may be warm enough for life. The planetary system, discovered in 2014, lies 3,000 light years from Earth. Although astronomers have found planets similar in size to Earth and stars like the Sun are fairly common, finding a temperate world around a friendly star is rare. This marks the 3rd confirmed planet in that solar system, and researchers suspect a 4th planet still awaits detection. More than 4,000 worlds are known around stars other than the Sun. These exoplanets are far more common than most people believed just a few decades ago. One question that perplexes astronomers now is why planets don't form around some stars. A new study of the Westerland 2 star cluster suggests that planets are less likely to form in systems where clusters of stars huddle close together. These regions were found to lack large clouds of cool dust, which normally forms the foundation of planetary growth around stars. Coming closer to home, but going back further in time, we learned that Mars, our friendly neighbor next door, may have developed and lost systems of rings several times over the last few billion years. By studying the orbits of the 2 moons of Mars, Phobos and Deimos, astronomers at the SETI Institute have determined these small potato-shaped moons are likely the products of an ancient ring around Mars that coalesced together into the pair of moons that we see today. This week on Astronomy News with the Cosmic Companion, we welcome Anna Ho of the California Institute of Technology. She recently contributed to a new study on F-bots, a newly discovered type of supernova explosion. Welcome to the show, Anna.
Thank you for having me on.
Thank you. So tell us, for those who may not be familiar, what are supernova and
How do they form?
Sure. So a supernova is a very energetic explosion that marks the death of a massive star.
All right. And so what sort of how are F-bots or fast blue optical transients different than normal supernova?
Well, they look different, and how they're related, I think, is still a mystery. But I can tell you a bit about why they look different. So a normal supernova basically looks like a new star in the sky. That we go to a part of the sky and we see that there's a star there that isn't normally there. And normally it takes a few days for it to show up. It kind of gradually increases in brightness, and then it hangs around there for a couple of weeks, and then it gradually fades away again. Whereas F-bots, so fast blue optical transients, so they're much faster than ordinary supernovae. So they kind of appear out of nowhere and are suddenly very, very bright. We call them blue because their colors are bluer than ordinary supernovae. And then they disappear quite quickly again, again faster than ordinary supernovae. They seem to, I guess that's really what caught our attention in the first place. And then what's unusual about some of the recent F-bots we've found is that they seem to be capable of, I guess they seem to have an unusual kind of afterlife. So ordinarily, when a star dies, it produces this corpse, so either a neutron star or a black hole, and that corpse, as far as we know, just kind of sits there. But in the case of F-bots, it seems that corpse remains active and is capable of launching some kind of outflow of material. And that produces quite bright X-rays and also radio waves months after the star has died.
So that's some pretty high energy radiation coming out of there.
Yes.
Sure. Yes. So by active, what is it still doing? What qualifies these stellar corpses as still being active?
Well, so we see that it's still, I guess, with the first F-bot that we saw that it was somehow producing, that there were somehow powerful X-rays being produced by this corpse, like I said, months after the explosion. We don't actually know the mechanism by which those X-rays are produced, though. That's one of the mysteries that we still have to address.
And how common do you think that these F-bot explosions are around the cosmos?
So that was something that, as part of my recent study, I tried to estimate, and it seems like they're actually quite rare. So initially, with the first one that was discovered, it was quite nearby, and so I think everyone thought, oh, it's so nearby, oh, they must be actually quite common. But then we've waited now for a couple of years, hoping to find many more, and really we've only found one more since then. So it turns out that they're rare. So they're actually, we know that most massive stars do not end their lives this way. This is a rare and particularly extreme kind of death that they can have.
And so what kind of stars are most likely to end their lives, or at least experience becoming an F-bot
Yep,
explosion?
That's the question now. Why would one star become an F-bot while another would just die, in the normal way? One clue is the type of galaxies that these are found in. So these are found in quite little dinky galaxies that have very high rates of forming new stars. The metal content of these galaxies is quite low. What exactly that means is not super clear, but one possibility is that stars that live in environments like that are capable of having much faster rotation rates of their cores. And so if the core is rotating much more quickly, then when the star dies and this core collapses, it'll spin faster and faster and faster. And you can kind of imagine that a fast spinning core is maybe more likely to launch one of these kinds of outflows than one that is not spinning so quickly.
Right. And of course, as as the core shrinks, it speeds up like an
Exactly.
ice skater bringing in their arms
Yes,
and
exactly.
speeding up on the ice. So what got you interested in studying these objects?
Well, I stumbled onto them by accident. So I was actually looking for something else. So I guess that's sort of how this sometimes goes. So I'm currently in graduate school, and one of the sort of rites of passage in grad school is you have to give a sort of, you have to make a proposal for what you want your dissertation to be about. So and that's kind of, it's called the candidacy exam. So I did this candidacy exam, I think it was May 2017. And I said that I was going to look for a particular type of extreme cosmic explosion. These are relatives to what are called gamma ray bursts.
Mm-hmm.
And gamma ray bursts, that's another example, probably the best studied example of stellar death that has an afterlife, where there's some kind of active corpse for some time after the star has collapsed. So I was proposing to look for explosions that were related to gamma ray bursts, basically. And I remember my thesis committee told me afterwards that, often in this work, you won't find what you were hoping to find, but you should be open-minded. And if an interesting new opportunity comes up, you should be, flexible about maybe taking that opportunity. And then sure enough, 1 month later, the first of these sort of, this was called AT2018 Cow, the kind of original, well-studied F-bot appeared. And I think many of us thought it was something else initially. So I thought actually that it was the kind of object that I had been looking for my thesis. And I thought, oh, that was easy. I just had to wait a month. And then one just appeared in the sky. And so I began working on it very intensely.
Thank you.
Yeah, exactly. So I began working on it very intensely, but it became quite clear quite quickly that this was something totally different that none of us had really seen before. But at that point I was invested and excited to keep working on it. So that ended up taking me kind of in a different direction. So yeah, I guess I started working on this kind of by accident.
That's good. And when when the first of these that were discovered in 2014, they're often referred to as weird supernovae.
Yeah.
And can you tell us, and so you also bring about studying these objects using a weird variety of telescopes.
Mm-hmm.
And can you tell us a little bit about these different instruments and and how you collect data and why you do that to study these objects?
Sure. So I guess the first thing to say is that when this class of F-bots was originally noticed, it was primarily people looking through old archival data. So this is data collected years ago, and then people would search it and look for interesting phenomena. But by the time you've noticed something, if it's years after it happened, it's sort of too late to actually figure out what it was. All you can see is you see that something was not there, and then it appeared quickly, then it disappeared quickly, and that's unusual. But what it was, you're sort of too late to figure that out. And so what we were waiting for, what you hope for, is that one will appear in the sky and that you'll notice it as it's happening. And then you can, marshal all of your resources to actually watch it unfold. So that's what we've been able to do now a couple of times. And the reason why you have to use different kinds of telescopes is that the explosion unfolds in a number of different stages. And there are different physical processes at work in each of these stages. And those different physical processes produce radiation in different parts of the electromagnetic spectrum. So early on, you might get optical radiation, so the kind that we can see with our eyes. But then over time, you might get X-ray radiation, radio waves. And so it's important to use different, and the way that astronomy works now is we have different kinds of telescopes specifically designed to see those different parts of the electromagnetic spectrum. So we need to bring together optical telescopes and X-ray telescopes and radio telescopes. These telescopes all have different designs because they have to, there are sort of different, they have to contend with different technological issues depending on what the wavelength of the radiation is. So radio dishes are huge. So I can, I've climbed around on radio telescopes that are the size of baseball fields,
Yep,
basically,
yep.
like a baseball diamond. I've climbed around on a 100-meter radio dish in Greenbank, West Virginia.
Wow.
And those are big because radio waves are big. So the wave itself, is like a meter, or say a centimeters to a meter long. So you need big telescopes for radio waves, and those basically look like giant satellite dishes. And then on the kind of other end of the spectrum, there are X-rays, which are tiny. And that poses a whole other issue. X-rays don't penetrate through Earth's atmosphere for the most part. So we have to send a satellite up into low Earth orbit. So those are the Swift satellite, Fermi satellite. These are satellites designed to pick up incoming X-ray photons from space. But it would be a whole other matter to launch like a huge radio dish up into space. So these things just have we use totally different kinds of instruments to detect different types of radiation.
Yeah, and so what studies do you hope to see in the future on these FBOTs?
Well, we certainly need more. I think the problem we're all dealing with now is that since they're rare, we have to wait. So the 2018 cow was June 2018, and then my colleagues and I found another one in September was it September 2018? Yeah, I think September 2018, and then we haven't found any since then. And so the problem is, if they're just trickling in one every couple of years, it's sort of hard to make fast progress. What we really hope for is kind of a big compilation of them, because that would sort of tell us what kinds of diversity is allowed in this class of objects.
Yeah.
So I guess part of it is that we need to find more, and we need to be very systematic in how we identify these things. So different astronomers will use different definitions for them, which I think has led to a bit of confusion on what counts as an FBOT and what doesn't. So I think going forward, I hope that as we learn more about these objects, we'll be able to delineate different classes in a more physically motivated way. I guess it's a bit similar to, I think of it kind of like zoology, like people going out into nature and discovering new kinds of creatures. At first, you're just taking notes on each individual one that you see, but eventually you see enough that you're able to kind of group them into classes and do some taxonomy. So I would say in this field, it's exciting to be in this field right now because we're just at the very beginning, where each one has its own sort of unique personality. But eventually we'll have enough of them that we can really begin to sort them out into different categories.
That's super. Yeah, so let's hope that we see some more of those happen. And
yes, I'd really like to see some more.
and let's hope that they're not too close.
Yes.
All right. Well, thank you very much for being on the show. It was wonderful to have you.
Hey, thank you very much for inviting me. This was fun for me.
Super. And that was Anna Ho, a graduate student at Caltech.
Next week on Astronomy News with the Cosmic Companion, coming June 16th, we welcome Dr. Matthias Suick, a research scientist at the SETI Institute, discussing his recent discovery that Mars may have been accompanied by systems of rings in the distant past. Please stay safe, stay healthy, and keep your wonder alive. If you enjoyed this episode of The Cosmic Companion, please download and share the episode on YouTube or on any major podcast provider. For more details on space and astronomy news, please visit thecosmiccompanion.com or thecosmiccompanion.net.